Yeah, okay.
Welcome everyone. Welcome everyone from wherever you're connecting. I'm very happy to host Mehrnoosh Sadrzadeh today, who will talk to us about language models generally and about specifically quantum machine learning for vision language understanding. So Mehrnoosh, take it away.
Thank you so much for inviting me. I'm sorry I was late. I thought it would start at 5 o'clock, sorry. But no, yeah, so let me just dive in without any further delays. This is joint work, a very recent joint work with my group in UCL. So it's a large number of people working on this project, or this project has quite a lot of offsets. Some people work on smaller subsets, but the core that I will present today has been done by these three people in red. Ion Kinlo, Tila Limerick-Stocking, and Theo Ayosif. And I'm leading a lab there called Quantum Learning Labs, and I've got a research chair by Royal Academy of Engineering. So it's quite a lovely way of looking at language that we work with in the group. So it's called linguistic arithmetic. So it's like doing arithmetics, but instead of with numbers, you do it with words. And in fact, the first ideas for this model go all the way back to the work of Ajukewicz and Bar-Hillel, who were, philosophers / logicians in Poland back in the 1930s. And they argued that you can calculate do calculations in language in very similar ways as you can in arithmetics. And I would like to demonstrate their idea just very quickly. So in the same way as if you have number 2, and if you multiply it by the number 3/2, the 2's cancel out and you get 3. In language, the same kind of calculations happens between things like nouns and verbs. So, for example, cat is a noun, and the verb, you treat it as the following rational: a sentence over a noun. For example, sneeze, which is a verb, you treat it as a sentence over a noun to allow the interaction between two nouns to happen in the same way as it happened between 2 and 3/2. So whereas there, the 2 and 2 canceled out, here the two ends cancel out. So the end of the noun cats cancels out with the end that we put in the type of the verb, and as a result, we get the type of the sentence out. So we say cat multiplies with sneeze, same way as 2 multiplies with 2/2, and then we get a sentence. Which sentence is it? It's the sentence cat's sneeze. So in order to do this, you have to assign types to words, which is what we're doing here. We say the type of cat is noun, the type of sneeze is S/N, and the type of sentence is S. But apart from this general fact, Ajukewicz and Bar-Hillel, they did not offer any formalization of the model. In fact, they made quite a few mistakes in the informal expression of the setting. And it was not until quite late, first in the 1950s, but really in the 1990s, close to the year 2000, that Canadian mathematician, Jim Lambeck, he actually came up with a lovely way of formalizing their idea. And he said, whereas the algebra of arithmetic happens in groups, so we're not talking about the whole arithmetic now, just the fraction that allows us to do the cancellation between 2 and 3/2. That comes from the fact that there's a group sitting between multiplication and division, right? And that group says for every element, for every rational number, there is a number that's its inverse. And this means that if I multiply the number with its inverse, I'll get the unit of the multiplication 1 out, right? So this is the group multiplication and the interaction with its inverse that allows us to do this calculation. And then so he sort of wanted to analogize with language. And I used to talk to him quite a lot, and he would say, it's very tempting to say, that the algebra of language, like the algebra of arithmetic, is also a group. However, there's one very big difference. And that very, very big difference actually led to very nice mathematical discoveries. And that is, whereas multiplication in numbers is commutative, right? It doesn't matter if you multiply 2 and 3 over 2 from the left or from the right. You can do 2 times 3 over 2 or 3 over 2 times 2. Whereas in language, multiplication becomes juxtaposition of words. As you saw, we put cats and sneeze together in a very special order. And this is not commutative. You can say cats to sneeze, but you cannot say sneeze cats. So then he went on to invent something.
I have one question.
Yeah, I was going to have a question as well. But Irfan, you go ahead first.
I was just wondering, so S is the sentence and S over N denotes sneeze because the whole sentence is cat sneeze, and you want to divide the noun to just say sneeze by S over N. Right?
Yeah, so what you assign as types to these words, it's at the discretion of the engineer of language. Do you see what I mean? But it has to be in a way that encodes the rules of the grammar of each language. So yeah, so you would say, for example, for a verb, it modifies a noun, right? So it has to take a noun and returns a sentence, because that's what the verb does. An intransitive verb takes a noun and returns a sentence by modifying the noun. So that's why we assign the type S over N to sneeze.
Okay.
Like, for example, to extend that, a transitive noun that takes, say, one object might be, might be more complicated, right? A type that requires 2 inputs in order to return a sentence, right?
Exactly. A transitive verb will have a different type, so you'll have 2 divisions in it. And then the sentence as a whole will have 2 multiplications and 2 cancellations. Similarly, the type of an adjective is different, type of adverbs, prepositional phrases, you will have to sit down and patiently encode the rules of grammar into these types. And
so my question,
yeah,
my question had to do with the pre-group structure you're showing here. I wonder if in the example of cat sneeze that you're just showing us, would it be correct? Well, it doesn't seem to me necessarily to be correct, but it feels as though in this instance, maybe there is a one of the inverses, but not the other, right? Is that a way to see it? Like there's a right inverse, but not a left inverse?
Yeah, let me introduce pre-groups. So a pre-group is quite an interesting object. I've simplified it here. Maybe I shouldn't. So a pre-group is a partially ordered group. You need to have partial order. And this equality that I've put here is actually an inequality. But how do we define it? So we say a pre-group, it's a group where you've got 2 inverses, left and right, whereby for every element P of the group, it has a left inverse, it has a right inverse. And when you multiply the element P with its right inverse from the right and only from the right, this will be less than or equal 1, the unit of multiplication. And similarly for the left inverse, if you multiply P with this left inverse from the left, it's less than or equal 1. And this is what enables you to do account holding for the commutativity.
Also, do the left and right inverses depend on the element? Because I see NR as well as PR there. So,
sorry, can you ask again your question?
Do the left and right inverses depend on which element you're talking about? Because I see there is an NR as well as a PR, so it's not a unique right inverse for everything, right?
It is unique. The inverses are unique, yeah. So so for every element, in language, let me see what I've got in my next slide. So for language, you've got to generate these pre-groups in a free way. So you start with a set of basic types. N and S is a very good starting point. Anatomic type N, anatomic type S, these will be your generators. You generate your pre-group freely, over multiplication and the left and right adjoints. For every type, you give a left and a right inverse, a left left and a right right inverse. Do you see what I mean? A left 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 and a right 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 inverse, and the multiplication of all of them. And then when a type hits is correct adjoint with the correct ordering, they cancel out. But you've got all adjoints for all types in that free pre-group, if you see what I mean.
Yeah, I see it actually.
Okay.
I got confused
Yeah.
about something else. Thanks. Yeah.
Thank you. Thank you. Let's move on. Yeah.
Yeah, so this is a very attractive theory. In fact, it was so attractive, a lot of people applied it to many different languages. And I myself did it for Persian, which is my mother tongue. Then I just did it for Hungarian because it was Mackay Fest in Montreal. And they wanted me to have a paper. So he's Hungarian. So I did it for Hungarian. Because Persian is a descendant of Sanskrit, I also did something for Sanskrit. It's quite easy to take the, preliminary fragment of a language and encode the rules into left and right adjoint. Is really enjoyable. I recommend it. People have done it for Japanese, for Italian. Lambeck himself did it for Latin verb conjugation. So it's quite fun. Shall I move on? Yeah, okay.
Yes, I think so. Although your mention of conjugation makes me think that, there's morphology here too. It's not just syntax, but we can leave that for later.
Yes, it's your choice how fine-grained you want to be. At the level of just words, you work with grammatical types. But if you want to do morphology, you have to go at the character level. And then you can introduce morphological types, which is what Lambeck did for Latin. You could work with both of them together to have a better view of grammar. Do you see what I mean?
Yes, like where the essentially the token can be a variable object that doesn't have to be, in other words, it can span different levels of the hierarchy, right? It could be words, but it could be also symbols, individual letters, or,
yeah. Later on, Lambeck, he came up with the idea that if you want to work with different analysis, you'll have multiple pre-groups, one for the word level, one for the subword level. You work with the multiplication of two pre-groups. Yeah, interesting.
Thank you. Well, yeah, please go on. Yeah, I'm sorry we delayed. We kind of slowed you down.
I can talk about pre-groups, for full talk. Quite entertaining. But I guess what we want to focus on here is that this is also an attractive theory. Its simplicity allows us to develop a homomorphism between pre-groups. And if you know category theory, category of finite dimensional vector spaces and linear maps. So in short, you've got finite dimensional vector spaces, you got their tensor products and its units, field of reals. And instead of the two adjoints, you got the dual space, V star. So then both categories, so pre-groups are also categories. They are what's called the thin category, right? Skeleton category, where the morphism between any two objects is the partial order between the two. So you got at most one morphism between any two objects. Elements are objects, for partial ordering is a morphism. Finite dimensional vector spaces are also compact closed categories. So pre-groups are compact closed categories, multiplication being the tensor product. Finite dimensional vector spaces are compact closed categories, and this baby can be seen as a functor between the two, the homomorphic passage. And this will assign vector space semantics to pre-groups. So this is as follows for atomic types, N and S. You will assign a vector of real numbers, right? If you have adjoint types, you will assign a vector in the dual space, a linear functional. And whenever you take multiplication, you do tensor product at the level of types in the vector space. As a result, any syntactic calculations at the pre-group, like cat's sneeze, is NRS. This will correspond to a calculation on the vector. So this will have a meaning in the space R, tensor R star, tensor R. We just assign everything inductively, compositionally. So that's at the level of types. But we can actually say something nicer than that connects us to machine learning. And that is, you can talk about not only the type of the word cat, which is N, and the space in which this type, has semantics, which is R. We can talk about the meaning of individual nouns in that space. So every word of type N, for example, cat, will get a vector in the vector space R, and we denote that vector by TI cats. So we put the name of the noun on the top, and because there's a vector, we have one index for this vector TI cats. If you have a compound type NRS, which is the type of your sneeze, then the meaning of every word with that type, all intransitive verbs, becomes an element of the tensor space R star R. What's that? It's a matrix. T sneeze IJ. So 2 indices IJ because it's a matrix, because it comes from this tensor space, R star tensor R.
Can I ask, Mehrnoosh, when this is being set up, are we purposefully leaving the dimensionality to be variable?
It will become a, yes, I guess so. It will become a parameter of the model. You work with the dimensions at the experimental level, whatever suits you. It's just the rank of the tensor that's important. That should match. And why should that match? Because the multiplication, this model multiplication that became tensor between the types should go through as tensor contraction between this vector and this matrix, which in this case is just matrix multiplication. Meaning of cats is a vector, meaning of sneeze is a matrix. We made the indices match. It went through because of this adjoint type was there. And that means the eye of sneeze and the eye of cats will cancel out, contract. You sum over the shared index, and then you get a nice, beautiful vector for the meaning of cats sneeze in R.
Yeah, so what I'm having in mind, what I have, yes, I do see this mathematically. What I have in mind, I was trying to think more philosophically from the linguistics perspective. Here's my very rough attempt. Please correct me because it's probably too rough. But something like, TIJ, the word sneeze, the meaning of the word sneeze, expects an input that might have a variety of attributes, and cats has essentially a meaning that fits all those attributes, and therefore they can sort of match as vectors. One as an input to the other matrix, right? Do you see what I'm saying? That they can. I mean, the fact that we want this mathematical structure to fit essentially implies that we're thinking that all the ways in which all the attributes, all the semantic attributes of cats match all the expected input attributes that sneeze has. Is that a way to think about it?
I guess this is how you should think about it. But at the end of the day, we don't care because we learn these matrices in such a way that the meaning of a sentence would work as it should. So you would require certain sentences to be semantically similar to each other or infer one another.
But I suppose here's what I mean. Just to be facetious a little bit, but I mean, cats could also mean, let's say, in colloquial language, the musical cats, right? Which cannot, okay. Right? For example, could have other attributes that are not specified. Like whenever we use language, we can use it with almost like, what I have in mind is like maybe a limitless possibility of meaning that words have, which means that over time or in different contexts, they can engender a meaning that wasn't, or an attribute, let's say, that wasn't there before. And so that might not match. So you can't a priori say they will always match in every instance. Do you see what I mean?
Yeah, you would want these things to come out when you learn meanings of these words, that the ambiguities in the meaning to filter out when you compose them together.
Okay, okay, that's good.
Yeah. In fact, if you don't mind, we've got quite maybe 3 papers on how to learn matrices for verbs and vectors for nouns, such that these ambiguities are presented in a modular way, so that the composition will disambiguate.
I
Okay,
want
sounds
to
good.
ask some
didn't
very
mean to- yeah.
basic question
Okay.
to clarify. So is it that for each word there is, so if it's a noun, then for that noun there is a real number assigned to it, and then if it's like sneeze, where it requires both the inverse of a noun as well as a verb, there is a function there's a function that we have to apply to the noun essentially to get the Tij sneeze. And so now the final real number you are getting is the product of the two real numbers, Ti cats and Tij sneeze. Is that the way this is explained?
Nearly, cats is a vector.
Cats is a vector, okay.
And sneeze is a matrix. If it was an intransitive verb, it would have 3 indices and it would become a cube. But the important thing is that the interactions between the words would become contraction between these tensors. But if you just have a matrix, and a vector would be matrix multiplication. So, but why does it work? Because a matrix is nothing but a linear map, like it's a map. When you multiply the matrix with a vector, you're really applying the map in a verb on the vector, modifying it. So this is what we're doing here. Sneeze is a linear map that takes a vector of cats as input and modifies it by making cats sneeze into a sentence which can be either true or false. Do you see what I mean? So
well, actually, on top of it, what the extra thing that you're saying, and maybe it will help you if I understand, is that when you contract, you get the same type as your input type. So you get another vector that can become an input. So in other words, the sentence that comes out, the sentence cats sneeze, could then become, let's say, a noun, between like as a noun phrase for something else. Is that part of the story here as well?
Yes, yeah, the compositionality it makes happen. In this case, cats sneeze becomes a vector, and that's a vector for a sentence, but it lives in the same space. Doesn't have to live in R, but I've just done this simplification that N and S both go to R. It doesn't have to be like that. I can send N to an atomic vector space called capital N, and I can send S to capital S. They don't have to be the same. Neither of them has to be R. Do you see what I mean? This I've just done the simplification here.
You mean those as the components of the vector? Basically, it's a vector space over R in some sense.
You could think of it this way. You could think of it this way. Yeah, vector over R. Yeah. Let me see what so I've got an example for the transitive verb. So for transitive verb, you got cats chase mice. Cats is this N. Mice is this N. And this compound type NRSNL is a type of your transitive verb. Now you see here, cats becomes a vector in R, mice becomes a vector in R, and the transitive verb becomes a cube in this tensor space. I've got a star on this R, and I've got a star on this R, and this means when I then form the contraction, there is a joint index, shared index between cats, I, and chase, IJK, between mice, K, and chase, the K of the chase. And this contract, and again, then you get a vector for the meaning of the sentence, a vector in R. And this will go, if I had adjectives or adverbs or prepositional phrases, I would have assigned the types so carefully that this would happen no matter how long or how complex the sentence is.
Quick question with respect to that. But this is maybe a couple of steps beyond what you told us. So I'm inferring, I may not be correct here. but that while this pre-group structure is capturing non-commutativity, which is essential in semantics here, it doesn't seem to, or it's not obvious to me how it would deal with the non-associative nature of language, where, you know, the parenthesization, or in some sense, you know, the syntactic trees, they're not that, you know, they have a natural parenthesization, which wouldn't necessarily be captured with this structure. Is that right?
Yeah, that's right. If you want associativity, you have to introduce brackets for the multiplication on the pre-groups.
Mm-hmm. Yeah.
Yeah.
Okay.
Yeah, indeed. Yeah. Okay. Now, the interesting thing is that, so we, why do we even work with vector spaces? And that comes from this kind of statistical models of natural language, where they learned embeddings for words based on co-occurrences, you know, between words in a large corpus. You write a nice machine learning algorithm and you learn a feature vector for words. And it wasn't clear what was the logic. So how, if the words composed to give sentences, what would the meaning of a sentence be? And it was also at the time not clear what was the right semantics for pre-groups. So by developing this mapping, we sort of solved two problems. One, developed a semantics, a nice vector space semantics for pre-groups, you know, the first semantics that was out there. And we provided a logic for this statistical models of language processing. There was only one problem left open, and that was, whereas language models, they learn vectors for every word, here we are requiring that certain words have matrices and cubes and hypercubes and so on, right? Because we here say an intransitive verb has to be a matrix, to sneeze. A transitive verb has to be a cube, chase. A ditransitive verb like give has to be a hypercube. Now, question is, how do we learn these higher order vectors? Vectors we know how to learn, but if it's a matrix, how do we learn it? If it's a tensor, how do we learn it? And so that was interesting, because for a long time, nearly like 10 years of...
Do you not learn them column by column or row by row? So what does a column of the matrix mean?
You can treat it that way, but I think the way we are thinking about it is kind of relational or functional. It's got to be a mapping that would take the meaning of your word and return the meaning of your sentence.
Okay.
It's quite interesting. If you think about it this way, you can use linear regression, or what we call
Well, you can do that. You can do that in function space, treating the matrix using, say, the L2 norm, or, you know, L2 norm on the function space, the linear transformation space, or something like that, or the soup norm or some such.
You can do it, and we've done this. We had a couple of papers on linear regression and then multi-stage for if you want to learn a cube, and then you have to go higher order, a hypercube. You can do it, but getting good quality representations difficult. You need a lot of computing.
Yeah, that's always the rub, isn't it?
But until this, we came across this tensor network theory from quantum mechanics, where you don't have to learn these tensors like you're describing as rows and columns. There you can use certain decompositions, and by doing that, you're imposing a structure on tensor.
Yes.
And then you can learn it effectively. You know, you can learn it, what they say, at scale. And this idea...
So you learn factors of it instead of columns.
Yeah, this was a breakthrough. I don't want to talk about tensor networks, but basically it came from many-body quantum physics, where a complex system with many tensors had to be computed, calculated, and it was nearly impossible. So people started to come up with factorizations. The most famous one is called matrix product state. So if you have an order n tensor, so I've written it down here, which we have dimensions d1 to dn based on the rank of each element therein, matrix product state reduces it to this formula. If each dimension, if each di here in the model formula, all di's are equal to each other, then this complex formula just simplifies to this one. B is the bond dimension, the number of shared indexes between the matrices. That's B. D is your dimension. And if B is 1, you only got one dimension. I'm just doing these simplifications to show you how good it gets. In the best case, then if you have D to the n dimensions for your tensor, it really reduces to ND. So you are doing reduction from polynomial, from exponential to polynomial. Now this is undesirable. You never want your one dimension to be 1. This really is not good. You got a lot of separable spaces. But you'll see, you just see the beauty of it. Instead of calculating some huge formula like this, you end up calculating ND, which is quite lovely. And matrix product state is not the only decomposition that's out there. There is other ways of decomposing. There is pocket decomposition, which gives you trees, and there's combinations of matrix product and tree. Yeah. So then we learned these decompositions are actually quite common in people who do scientific calculations. These tensors are used at large and for complex systems. This image I took from a paper in biology, and these are, you see, all these different decompositions they work with. And by far, these are not just the only ones. This tensor decomposition theory has also even been applied to compressing internal weight matrices of large language models. There are libraries out there, packages you can just apply to the weight matrices. And so, yeah, so then this is what...
Can I ask, sorry,
Yeah.
Mehrnoosh, what would any of these take as an input? I mean, you'd have to specify first the vectors, no?
You just, these matrices, these tensors that we were learning here, look here. So for example, we would be learning, you want to learn a matrix for a cube for chase. So instead of learning the full cube, which is what we did using multi-stage linear regression, you apply matrix product tensor decomposition to the tensor of the cube. And then you will have to learn 3 smaller matrices that contract with each other. Here you see in Alice Loves Bob, you can see. Yeah. So that's basically, this became the bread and butter of this line of work. There are packages out there that would decompose your matrices, and then you could learn them with much less effort than just brute force learning them directly. Yeah, so I have example. So this vision language models, as in the title of the talk, is the most recent application we've been working with. But in the meantime, we've applied these models to also language-only tasks, which I won't talk about because they're boring for me now, because vision language is much more interesting.
So what should we have in mind as an application? Instead of words now, we have images, and you want to instead of the matrices transforming words into sentences and so on, we have ways of transforming images, like the different ways that a dog might look, for example. Is that something to think about?
Yeah, good question. So visual language models have 2 components, text and images. And the idea is to align the right text to the right image. So you see a picture of a dog, you want to say the text dog. Or you want to go more complex and say a dog is sitting on some green grass. So the idea here is, at the moment, let's leave the image alone because we are working with the theory of language. We have grammar, pre-group grammar for the language side. So we say, let's analyze the text part of these models compositionally. You apply pre-group typing, you get, your types, you apply the homomorphism, you get your tensors, and then you learn these tensors by tensor decomposition. After you've done that, then you will do exactly like the normal models. You'll have a vector for your sentence, right? But this vector is built compositionally. You have a vector for images. This comes from a transformer. And then you match them. You see how close they are. If they're very close, you say this image and this text are aligned. Do you see what I mean? And if they're not, you say they're not aligned. So that is your task.
So this is the this relates maybe to Matt's earlier question. Does it make a difference how you measure nearness in terms of either the efficiency or computational complexity or, yeah?
Yeah, so that's a good point. For a long time, people just take the Euclidean geometry of the space. So you work with cosine distance. If the vectors are normalized in a product of the two vectors of the text vector and the image vector. And that's where your learning happens. Do you see what I mean? So you train these matrices and tensors for the text side in such a way that when you compose them, you get a vector for the sentence that is geometrically close to the vector of the image. And for now, the vector of the image just learned no composition, no structure, using your normal transformer. They work really well. In fact,
yeah, so I wonder if any research, if you're aware of any research, or maybe this is where you're going, where imposing a different geometry in that space might make the comparison more effective, or the learning, it might converge better or faster or something.
Yeah, good point. So a recent set of papers are emerging, but they're very recent, though, that they argue, because here you've got multiple modalities, then it's not good to work with Euclidean geometry, and maybe you have to work with a manifold of some sort. Maybe the space is warped, you have to go on the curve, and the direct distance is not good. Some people say maybe this doesn't have to do with the presence of many modalities, but that images and text live in different spaces. So image vectors are completely different from the text vectors.
Do you consider any situations where the properties of your distance, that it loses certain desirable properties for larger distances? Because one of my collaborators and I came upon this with a numerical method, not in machine learning, but we eventually found out that for a particular algorithm we were working on, if we defined a distance between they were chemistry profiles, so energy pair particle separation distribution profiles. And we found that if we were within, I think it was √2 units of distance in the distance function we defined from a solution of the problem we were looking at, then it was a metric within that region. But outside the region, it failed the triangle inequality. So do you have some things like that? But I think that might be quite that kind of idea might be quite applicable in the abstract here, where your machine, where your algorithm has to learn whether or not the distance has those properties close enough to a minimizer of your optimization algorithm. Is that?
Yeah, I feel like I don't know how to reverse engineer it, but I do feel like a simplistic cosine similarity might miss out on essential properties.
Oh, okay.
Get some very important differences between text and image. And that if you use cosine for what's called contrastive learning here for visual language, there are limits to learning that you will never be able to overcome because you're simply just ignoring a big part of your space.
You're right,
But,
right.
you see what I mean?
Also, I think what Matt, what I'm getting from what you're saying, I think what he might be implying is that, you know, in some sense you have two different vector spaces, you know, that you're trying to match, like they're locally, you know, locally isomorphic, let's say, and you're trying to match them, but there's no reason to think necessarily that you can globally match them with, you know, embed them within the same metric, at least not, you know, in some realistic space. And so maybe having, you know, giving up on having one metric that will always work, and sort of almost like it makes me think of these kind of multi what are they called, sort of you know, multi-scale kind of models, where essentially when you get near enough, then you have a nice metric of a particular kind to do the you know, your optimization. But if you're, you know, farther away, you know, you could use other methods. Like you don't assume that the same metric would work equally well everywhere.
Yeah, this
is similar to manifolds anyway, and that's part of the reason I brought it up, as you mentioned manifolds. That you have local metrics on a manifold, but it's very common for the manifold one's working with to have a global metric as well, and that global metric determines geodesics in the whole space. But a local metric on a region around a point then has a different way of measuring distances, and so possibly some different geodesics than the restrictions of the geodesics from the whole space. That might depend on the way that the manifolds that the metrics match up, and indeed in I think in differential geometry and so forth, where they use these things, these Euclidean manifolds, I think they set it up so that the geodesics do match up on the local patches when you intersect the geodesic from the global space. Anyway, it's starting to get far afield. I didn't mean to pull you off track too much. Sorry. Thank you.
No worries. No, this is very new. And that's really interesting because statistical people don't really think about the concepts underneath. And a bunch of new papers have come out by philosophers thinking about alignment in space and how it should be. Yeah, I don't have a right answer for it, but definitely I feel like Euclidean space is too simplistic. Okay, shall I carry on?
Please do.
Yes, please.
Okay. So, right. So this, right. So, you know, so this, it was interesting that visual language models, like language models, were around for not a long time, but it was not until the invention of large visual language models that they made a difference. And like large language models were initiated by OpenAI. Large vision language models were also initiated by OpenAI in 2021 when they introduced a tool they called QuCLIP. CL is for contrastive learning. Which is exactly this architecture you see here. You train transformers to learn vectors for images and text, and you learn their alignments by calculating their cosine. Now, just shortly after their conception, people found out that these models do not understand the semantics of the images, neither text, and a bunch of data sets came out. So I'll have an example of one of these here. So this is called the ARO data set. So if you have this image, you know, and then you have the text, the post is right to the right of the building. And if you just then render the text by saying the building is to the right of the boss, the vision language models, you know, CLIP cannot distinguish between the two. It can distinguish the boss is to the right of the building from the sky is blue. Do you see what I mean? But it won't be able to reason structurally about, you know, a simple rendition of the image or the text. Similarly here, silver fork and brown icing won't be recognizable from brown fork and silver icing. So if you change the...
Is it because it doesn't have the algebraic structure that we previously talked about with words?
It has no structure. The transformers just brute force.
Right.
You know, they brute force learn vectors for descriptions, and they don't take structure into account. These vectors are highly non-compositional. So this is where we could add value. And so we said, well, let's, like I was saying, forgetting about the image, let's just freeze the vision transformer and just look at the text one, where you do what I suggested. You see what I mean? So you learn an embedding which is learned compositionally using pregroups and then tensors. So that's this nice. So we changed the architecture. We called it DisCoCLIP, Disco for distributional compositional. And this gave such very good results. I'll show you the table of results. So let's just look at one of these baselines. It's the ARO baseline. So in the ARO baseline, as I said, this is what you see, the images and kind of warped structured text corresponding to them. And the table of results, look. So I've divided this into quantum and classical. Quantum because we use tensors. So yeah, the classical model, the CLIP model. Tell me.
But it's just a quick question. But tensors, but always over the reals, whereas in some other instances in quantum NLP, you know, they use, you know, complex vector spaces as well.
No, good point. Something... So it's very interesting because the tensors, you can just learn the tensors and then you don't have to work in the complex space. I'm also going to present some work where you transform the tensors into variational quantum circuits, and then you're learning in the complex space. So for this table, it's just tensors. Like we call it quantum. We shouldn't have. It's just quantum inspired. This is just over the reals. It's not complex. We've just taken structure into account. And if you just look at ARO, just forget about the first part of this table in the interest of time. If you see like CLIP does 61% and we do 70, CLIP does 51.53 and we do 55. So it's quite a large improvement. You get just by imposing structure on the text. Yeah. This is basically.
Is this to be compared to? I mean, is there a linguistic comparison here that we should keep in mind, or is the difficulty the fact that the semantics of images are different from the semantics of language, or is it that we can impose a similar algebraic structure to cover the semantics of the visual images?
No, good point. I feel like we said there is enough structure in the linguistic description that even with only that structure, you can go a long way. So true that the images are frozen, but enough structure will be represented by the language side. We are now also imposing structure on images. We wish to write a paper saying 2 structures is better than 1. But this is to be proved. I mean, we are not actually quite sure. We were sure before running the experiments, But now we are not so sure. Maybe one structure, linguistic structure is very strong, and it's so easy to get structure out of language. Images are much more difficult because you got grammar for language. Whereas for images, you have to do entity recognition, and the relational connections between the entities are not present in the image. Well, I can talk about this forever. So what do I have on my next slide? Yeah. So interesting is we can ask the following question. What if I just use tensors? I just do a matrix product state for my words. I will not learn matrices, neither cubes. Everything is a matrix instead of a vector, and then you just do tensors, the matrix product state, but it still doesn't have any structure. So that's the spider model. And as you can see, spider model worked at chance level 50%. So it's not really the tensors that make you win. It is the structure. And the tree structure that you see here, together with compact, they did the best. Finally, my last slide. This is interesting. So there are newer friends to CLIP. One is called OpenCLIP, which we won. We outperformed OpenCLIP. And then there's another one called Blip. And you see, we do not always beat Blip. So in ARO attribution, we don't beat Blip. And Blip actually does quite well without any structure. Now, my question to you is why? Can you guess why? If you know your transformers, you should be able to guess.
Which we don't, but can you tell us a little something about how B is different from C?
No, good point. Okay, so it's because of the parameter difference. So Blip was trained by introducing
it's much larger space.
Yeah. Parameters, yeah, huge, much bigger. So I've got a parameter comparison. So look here, CLIP has 63 million parameters, similar to OpenCLIP, but Blip has 137 million, twice more parameters. It was basically trained with many different objective functions rather than just contrastive learning. So parameter space increased. But then this also brought us to the following fact that our models use very little parameters. So this compact model, this one, that got very good results, on ARO is 28 million instead of 63. And on another benchmark, only 500,000. Which is quite pleasant. So yeah, if there's time, I can also tell you about the quantum variance, because these tensors are still learned classically. Do you have any question on these two slides, on the results and the parameters?
No, I think I'd like to hear a little bit about the quantum learning, if possible, for for a few minutes.
Okay, so the quantum, so we say, well, okay, tensors can be learned classically, still quite an effort, but you can manage. But if these tensors are actually taken to circuits, so you can very easily translate a tensor to a variational quantum circuit. Then what we are learning is a quantum state for text and a quantum state for the image. And then the distance that we were talking about, you can have to calculate overlap between these states, and a measure such as fidelity is useful there. Basically, your norm.
What is that? Yeah, is that fidelity? Some sort of what kind of maps are you imagining here? Because that's yeah, I mean that inner product will be some sort of complex number, and then you're mapping it onto, is it a 0-1 map? I mean, is it a mapping into the unit interval or something, or?
So if your states that come out of your circuits are mixed states, you can take the Hilbert-Schmidt norm, and it's very similar to cosine, to inner product.
But so it's between 0 and 1, basically. Yeah.
Yeah, but if the states are pure, then you have density matrices, and then you have to take the square root of the trace of the density matrices multiplied with each other. And that would then give you something very different. So still, if we design the circuit such that we will get mixed states. And so we use the Hilbert-Schmidt norm. But some people, they don't, because if you want to run this on hardware and you have restrictions at the hardware, you don't want to do what we call post-selection at the quantum level, and you want to use discards, if you mix this pure states. But we want to, because we thought Hilbert-Schmidt is much better measured than the complicated trace overlap. So because these are not really quantum, these are not, it's true that we're using tensors, but it's not really quantum data. So it would not really make sense to work with proper fidelity and pure states, if you see what I mean. So that's what we did.
Also, I mean, it's the Hilbert-Schmidt is much more efficient as well.
Yes, much easier to calculate. So I've got a few more slides just to say, because so far I've shown you how to go from pregroups to tensors, but you can also go from pregroups to variational quantum circuits directly. Well, I won't have time, I'm getting a bit tired, so I won't have time to explain this. But there is a nice mapping between pregroups and variational quantum circuits. So I'll just throw this at you. From a pregroup derivation, you get a nice circuit. And that's what we have done now. This made me realize I'm showing you the wrong slide, so let me stop sharing. I'll find my right slides. The table of results. Okay, so let me share my screen again. Okay, sorry, just showing you an old set of slides. Oh no, this is also. Oh no, not sure what's happening. Anyway, I can't show, but so if you go directly to circuits and then you do variational quantum circuit training, the number of parameters here substantially reduces. So whereas here the compact model, which was our best model, has 500,000 parameters, there you just work with 10,000 parameters. The accuracies stay more or less the same, but the number of parameters hugely reduce. Yeah, that is.
Do we have any sense why that is?
Yes, it's very interesting. When you do tensor learning, you have this freedom that you can work with the dimensionality of your tensors and the dimension of the bond. And often it's not the smaller dimensions that work. So you still need quite a few parameters to fill that tensor. But when you go to quantum circuits, as you can see, here, these are the better model, but a handful of parameters suffice. So for this U map here, so the U map is basically a tensor for a transitive verb, which was the cube. You just need 2 rotation angles. You just need 2 parameters. You can repeat this configuration and say, I'm going to do some Hadamard, some controlled rotations, and then you can repeat it. And you can say, maybe I want to have another layer of controlled rotations. That would make the number of parameters increase from 2 to 4. If you want 3 layers, it would go from 2 to 6. Do you see what I mean? It increases really linearly. And we didn't do more than 3 layers. So the quantum mechanic formalism really tells you do not need to learn this tensor really element by element. It's true that you have factorized it, but you don't even need to do that factorization. You only need, some of these models only have 1 C naught, so you only need a few rotation angles to estimate it.
That's interesting. I mean, it uses in some sense the universality structure of XZ calculus essentially to take advantage. You know, you're taking advantage of that. But I wonder. I mean, this seems like an empirical fact. You know, that I wonder if there's any theoretical understanding of why that is. You see what I'm saying? I wonder.
Good question.
Yeah. What is it telling us about the structure what is it telling us about the hidden structure of the semantics we're interested in? The fact that this algebra is so efficient at encoding it.
I feel like this, I want to say, is entanglement is explored to a much larger extent using these models, and then
That's right. That's where my mind was going as well, in terms of the contextuality that is captured there with entanglement, and that in some sense that maybe the appropriate sort of structure for the meaning creation that we intend, you know, in the sentences or in the visual space or in the combination of the two, that that is just more efficiently captured with these structured introduction of entanglement that let's say embedded C0 gates or these embedded rotations do within the variational circuits. But it's I wonder from, I mean, you know, it's a broader kind of question, more to do with I suppose philosophy or linguistics, or, you know, in terms of like, what are we learning from this very kind of application driven pursuit of, you know, faster computation? What if we're learning something about the thing we're after, you know, the property of the thing we're after, which is how to understand semantic space better.
Yeah, I feel like a good philosophical analysis of this setting is still lacking. And it's open to philosophers to help us. I've got one very interested student this year who is a physicist, in fact, but he is interested to work out why this works. Yeah. For entanglement, you can come up with some very nice arguments. And there are papers out there. I don't find any of them convincing, but it sort of says, if you want the meaning of your sentences not to be separable to the meanings of the words they're in, then you ought to use entanglement. Yes, yeah. But the fact that circuits learn tensors much better is not a surprise. I don't know how much more can we push this. I feel like, I mean, I like your, how do you call it, bravity, your courage. I don't think there is a philosophy out there. They're like, just like tensors are learned better using circuits, because you've changed your space and you just need less elements to understand them. Maybe. If this is connected, I mean, the space of language,
the space itself. Yeah, I was going to say that the trade-off is the space itself becomes very big, but the elements you need to describe it are fewer because there is more structure to it.
Yes, that's a good way of looking at it. Yeah. Maybe we still have to understand. We're trying to visualize now the block sphere where these things are learned. So you would have an idea of what is happening where.
In the meantime, I want to read out also a question that Matt put in the chat, and he's talking about how do we encode the vectors from the images, whether in the quantum or the full tensor framework. And he says, for relationships between images, do you ever consider them as elements of a space of closed subsets of a continuum. For example, thinking of the unit square in the plane as the view field, objects may reasonably be modeled as subcontinua of the unit square. The collection of these constitutes topological space using the Vietoris topology, and it supports various metrics, for example, the Hausdorff metric and so on. So I wonder, this is more like computational geometry type of questions. Is there anything you can tell us about how we go from images to vectors from a topological perspective?
I can't, but we are exploring now learning structure of images, and all these questions are in the air. But I don't know. I wish we could reverse engineer and just assume one of these, argue that one of these spaces is a better one for images, and then just learn the embeddings according to that. But I don't have a feeling, you know, my background is more language than images, and I do not have a feeling for these image vectors. All I know is that they're even more jumbled up than the word vectors.
Right, right. No, I mean, you were right. It really resonated with me what you said earlier, that that in the case of language, we have grammar, which is non-trivial. The fact that we have learned grammar and we can use that as the substrate on which meaning might rest, as opposed to just raw data. And in fact, to some degree, in my opinion, and now this is sort of going farther afield, but in my opinion, this is where some of the computational linguistics approaches fall short, is to the extent that they don't utilize enough of what we know about grammar and syntax. You know, if they just try to do it purely from the data, you're missing out on so much more structure. And I think my instinct is that much of the success that you're finding in your approach and in this Lambeck kind of categorical linguistics is because he put that in, you know, already from the beginning.
Yeah, I couldn't agree more, definitely. And I feel like it's the smoothness of pre-group grammars that have allowed passage to vectors and then tensors and then quantum cycles. And if you take just any grammar, the passage wouldn't be so simple and you wouldn't be able to push this through. So I think it's the simplicity, succinctness of the algebra actually has helped pave the way. But I have to go shortly.
I was going to say, yeah. First of all, I mean, let's very quickly ask if there's any other questions quickly from the audience. All right. Well, let's thank Mehrnoosh for a wonderful talk, a really far-reaching talk. Thank you so much for joining us. I mean, I think I'm left with a lot of very interesting ideas I'd like to pursue. I think it's the best place to be. I hope this was enjoyable and interesting for you as well.
Sorry I was late. We'll be very happy to discuss later if you have any ideas on the image. So I definitely send me.
Excellent. Yes, yes. And if you could, at some point, I'll reach out to you afterwards, but you can share your slides maybe so we can make them available to the listeners. Thank you so much. And good luck with your work.
Enjoy the weekend. Bye.
Bye. Thank you.
Bye. Thank you for the